you have to look at the recording to see what did they miss. Okay, so today we're going to start off with chapter 13. So chapter 13 is the general rule of probability. So the first rule of probability that we're going to go over the general addition rule. And the general addition rule, this is for when you have data sets that are not mutually exclusive. So if you remember, for data set that is not mutually exclusive, the Venn diagram that we drew for it looks something like that. Well, it looked a little bit better than that. But that's for mutually exclusive. So that means A and B, they don't share anything in common. So what we're going to do today, we're going to do, oops, sorry about that. We're going to do when A and B, they do share something in common. And when they share something in common, we usually say that's A and B. All right. So if you look at the middle portion, this is what the shared information is. So that's represent A and B. Cool. And the symbol for and is this symbol, which is upside down U or the intersect. All right. Any questions so far on the Venn diagram? All right.
So like the middle, like that's supposed to be A and B since they're both sharing like a middle part.
Correct. The red portion that I highlighted, that's supposed to represent A and B.
Okay.
So that represents the probability of A and B happening at the same time.
Okay.
All right, so let's move on down. So if you notice right here, I put two formula for you. So if you don't really like the notation, like the U and the upside down U, you can just use the first formula. So if you look at the first formula, it says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So the reason why we had to subtract the A and B is because, kind of think about it, like when we find the probability of A, we get this portion right here. And then when we find the probability of B, we get this portion over here. But if you kind of notice, when I was getting the probability of B, I pretty much counted this twice. So since you counted twice, to make up that you double counted it, you have to subtract by the probability of A and B. So anytime you have events that are not mutually exclusive, you have to worry about the overlap. So you have to subtract whatever the overlap is. So that's the probability of A and B, and that's why you subtract it. All right. Any question in regard to that first formula? All right. So the second formula is exactly the same thing. The only thing is I'm just using the notation. So instead of or, I'm just using the U. And instead of and, I'm just using the upside down U. Any questions so far for any of those two formulas? All right. So let's do this very first problem. So this first problem should be hopefully simple. So use the information that for A and B, we have the probability of A is equal to 0.40. The probability of B is equal to 0.30, and the probability of A and B is equal to 0.10. So one thing you kind of should notice, hopefully, anytime they give us a probability of A and B, pretty much they're letting us know they're not disjoint. So anytime they give us a probability of A and B, you should automatically know that we're dealing with events that are not disjoint. So that means you have an overlap. So if you look at the problem, it says find the probability of A or B. So if we want to find the probability of A or B, we want to get the probability of A added to the probability of B, and subtract it from the probability of A and, ooh, that's an ugly B, of B. Okay. So for this one, what does it tell us the probability of A is equal to?
Point
0.04.
1,
Yeah,
04.
so 0.4 or 0.40. What does it tell the probability of B is equal to?
0.3.
0.3 or 0.30. And lastly, what does it tell the probability of A and B is equal to?
1.
Yeah, 0.1. So if you do 0.40 plus 0.30, that will give you 0.70. And then if you do 0.70 minus 1, you get 0.60. And that's it. All right. Any question for that first problem? All right, so let's go on to the next problem. So for the next problem, it says studio and genre of movies. So it says about 20% of movies coming out of Hollywood are comedy. Warner Brothers had been the lead studio for about 9% of recent movie, and about 2% of recent movie are comedy from Warner Brothers. So it said, let C denote the event a movie is a comedy, and W denote the event a movie is produced by Warner Brothers. So for part A, it says write probability expression for each of the 3 facts given in the first sentence of the exercise. So the 3 facts are the 20%, the 9%, and the 2%. So where you go ahead and just label what do each one of these represent. So the probability of 0.20, probability of 0.09, and probability of 0.02. So what does the 20% correspond to? And if you want, you can type it up in the chat.
All of the movies.
But what type of movie?
Comedy.
Comedy. So for this one, we'll put C. So C for comedy. Oh, well. Let me do something. I think I. All right, so C for comedy. What about for the 0.09? What does the 0.09 represent?
Recent movies?
Well, what type of recent movie? Like who produced the recent movie?
Warner Brothers.
Warner Brothers. So we're gonna put W. All right. And lastly, we have the 0.02. What does the 0.02 represent?
Comedies from Warner Brothers.
Cool. So comedy from Warner Brothers. So that means C and W, doesn't it? Because if it's a comedy from Warner Brothers, that means it's a comedy and it was produced by Warner Brothers. All right. So everything is nice and labeled. Any question on how we label the percentage? All right. So one thing you should know, as soon as you see this, that we have an and statement, that's telling us that it's not a disjoint event. So let's go on to B. So for B, it says, what is the probability that a movie is either a comedy or produced by Warner Brother? So right here, the key word is or. Okay, we want it to be a comedy or it was produced by Warner Brother. So that means we want to do the probability it was a comedy or it was produced by CW, or sorry, by Warner Brother. Any question on why that's the probability that we're looking for? All right, so let's go ahead and find that probability. So for this one, you have to find the probability it's a comedy. We have to add this to the probability is from Warner Brother or produced by Warner Brother, and we subtract by the probability it will produce by well, it's a comedy and it's a Warner Brother produce. So for the probability of the comedy, you're gonna put 0.20. The probability is from Warner Brother, you're gonna put 0.09, and you can subtract that by the probability is a comedy and was produced by Warner Brother. Right. Any questions so far? I put 0.20 plus 0.09 minus 0.02. All right. So
0.27.
cool, 0.27. Or you could just say 27%. And that's your final answer. Any question for B?
Yeah. So if it was not or, and if it would say like that a movie is either a comedy. Never mind. Just ignore this. Yeah. Never mind.
All right, I'll ignore that. All right, so what I want you to do, I want you to do the same thing, but now do it for this second problem. So for this one, there should be two events. So the event should be, so I want you to find me the probability they're in band, probability they play sports, and the probability that they participate in band and sports. So I just want you to take a minute and try finding the probability. If you get stuck or anything happen, yes, in the chat, just chat me up, and I'll try to help you on the chat. Or if you want, just speak out loud and I'll help you.
Did you cut your own hair?
Yeah. What? Can you notice?
Yeah.
Just a little bit.
But it's okay. Like it looks good.
Yeah. No, it's just my hair was getting so long, and I didn't really want to go to the barber, so I'm like, let me just cut it, and that way it will last a long time. Cool. Good job, Valerie. So let's try this out. So for band, how many students participate in band?
85.
Oh, 85. How many total students do we have?
320.
Yeah, 320. Perfect. So, oh, take that apart. So let me just quickly do that in the calculator. So we'll do 85 divided by 320. And you roughly get 0.2 6, 5, 6. All right. What about for sports? How many students participated in sports?
20.
How many?
20.
Let's try that again.
20.
Not 20. You're missing something.
200.
Yeah, the 200.
Oh, sorry. Misread.
Yeah, no.
I didn't write it all down.
Come on.
Yeah, I figure. Don't worry about
It's morning. I'm tired, man.
it. I know. After a week off. Anybody go to any interesting place?
No. I was playing
And-
Animal Crossing.
Well, virtual places. Okay, let's go back. So how many people participate in band and sports?
60.
Yeah, 60. Yeah. Oof. Sorry about that. So we go 60 out of 320. So let me do 60 divided by 320. All right. Everybody go with that so far?
Yes.
Okay, so if we look at the last sentence says, what is the probability that a student is involved in either band or sports? So the keyword here is or. So we're gonna find the probability they participated in band. So band, I'm gonna put B for band or sports. So we're gonna find the bus. So all we have to do, we have to add these two values and then subtract it by this value over here. So we're going to say 0.2656 plus 0.625 subtracted by 0.1875. All right. Any question while I'm adding those two values and then subtracting by 0.1875? Right. So let me go ahead and just quickly do that. So you should get the probability that they're in band or sports is equal to 0.7031. And that's your final answer for that problem. Any question in regard to how we did that problem? Okay, so I'm going to show you a different way how to do this problem in case you don't want to use the formula, in case you want to use the Venn diagram. So we're going to do it using the Venn diagram. So okay, did not get my box. All right, so this is for band. So the red is band, the blue is going to be sports. So when we're doing a Venn diagram, you always want to do the middle first. So let's do the middle. How many students participate in band and sports?
What? Sorry.
So how many students participate in band and in sports?
0.1875.
Well, right now, just give me the actual students.
60.
Yeah, 60. So you put 16 here in the middle. All right. So how many people do band?
85.
85. So what we're gonna do, so this entire red portion should be 85, correct?
Yes. The whole thing.
The whole thing should be 85. But if you look right here, don't I already have 60 over here? So
Yes.
if I have 60 students right here that play band and sports, how many are left over that only do band?
25.
25, good. So these 25 are students that are yes in band. These 60 are students that are in band and sports. But if you combine both of them together, you get the 85. So
Okay.
what we're gonna go ahead and do, we're gonna go ahead and do now sports. But any question, where did the 25 originate from? Okay, so let's do sports. So I already have 60 students right here that are doing sports. But how many total students do I have that do sports? So how many total students do I have that do sports?
200.
140?
Yeah, so 140. So if you do 140 plus the 60, now you get the 200. So
Okay.
the 140 are the how many students we have that only do sports. The 60 are the students that do sports and band. But combined, you get 200 students that do sports.
Okay.
So any questions so far how I got this 140?
No.
All right. So let's go ahead and add this. So if I do 25 plus 60 divided, well, plus 140, what do I get?
320.
Let's try that again.
225.
225, there you go.
Kid doesn't know how to add.
My bad.
We all have those
It's
days.
early. Okay. So you have 225 total students. How many? Well, we have 225 total students who play in band or participate in sports. How many total students do we have in class or in this high school?
320.
320. So let's do 225 divided by 320. Then you get 0.7031.
So this is just another way of doing it.
Correct. So this is a different way how to do it. But if you look at it, both of them give you the same answer.
This way seems like a little easier. Like the other one, I got the other one, but this one seems like a little faster.
Yeah, it kind of depend on you and like how you learn. So that way kind of show both ways. So if you like the first one with the formula, you could use the formula. But if you're more like of a visual person, just like drawing stuff out, you might like the second one.
Okay.
All right, but that's it for the second problem. Any question for the second problem? All right, so let's scroll on down. Okay. So up next, we're getting to 13.2. So for 13.2, we're going to start doing something called multiplication rule. And the multiplication rule, we usually do this for independent events. So the first thing we're going to get into, what are independent events. So when we're looking at independent events are events that one event doesn't influence the second event of occurring. So when we're talking about independent event, one event shouldn't influence the probability of the second event occurring. So an example of that, say, well, let's do this first example. It says John wrote a 6 on a number cubed on a die, and then flip a coin that come up head. So he first rolled the die, and then he flipped the coin. All right, so they first roll a die and then they flip a coin. So say the coin, it landed on 2. And then when they flipped the coin landed on, we'll say, on heads. The fact that the cube landed on 2, does that affect the coin from landing on heads?
No.
Yeah, no. So since it doesn't affect it, we're gonna say these are independent. So that's independent event. Any question on how we got that to be independent? All right. So let's do the second one. So for the second one, said your teacher chooses one student to lead a group and then chooses another student to lead a group. So say we have a class, and this class, let's say it has 6 students. So we're gonna pick the leader for group A, but we're also gonna pick the leader for group B. So when I'm choosing a leader for group A, how many options do I have to choose from?
6.
Cool, so I have 6. But of those 6, how many of them am I gonna choose to be a leader?
Mm,
1.
Yeah. So the probability that I choose somebody to be the leader for group A is 1 out of 6. So say I choose this person to be the leader for group A. So he's the leader for group A, or she's the leader for group A. So now I have to choose a leader for group B. Is it possible that this person could be the leader for both groups?
yes.
No.
No,
But-
because it's picked already.
Yeah, because essentially since I already picked that person to lead
Oh,
group
okay.
A, I
Okay.
really wouldn't want to choose that person to lead group B. You kind of want somebody new. So
Okay.
I'm not going to choose that person. So now, how many people do I have to choose from?
5.
5.
You have 5. How many of them would I actually choose? How many would I choose to be a leader?
1.
1.
1. So from when I chose the first person to lead group A to when I chose the second person to choose to lead group B, did the probability change?
Yes.
Yeah, so the probability did change. So that will make this dependent. So if the probability would have remained the same as 1 out of 6, it would have been considered independent. But since me actually selecting a person and not being able to select that person again changed that probability, that's why I consider it dependent. All right. Any question why that one is dependent?
Oh, so like, what was the thing for independent? Sorry, because my internet cut out at that point.
Okay, independent just means that the probability for this event doesn't influence the probability of the second event. Because what's the probability like that it will land? So for the first one, what's the probability that the cube or the die will land on 2?
6.
Well, 1 out of 6.
Oh, 1 out of 6.
But does that affect the probability that the coin will land on heads?
No.
No, because they'll be 1 out of 2.
Okay, okay. That makes sense. Thank you.
All right, so let's try the third one. So for the third one, it said the battery in your cell phone is dead and the battery in your calculator are dead. So here, let's draw a cell phone. That's my best cell phone. So cell phone is dead, and then your calculator is also dead. Ooh. All right. So does the fact that your cell phone is dead, does that make it more likely or less likely that your calculator is also dead?
Not sure.
Well, does your cell phone battery depends on the
Oh,
on the battery
no.
of the calculator?
No.
No, it
That's
doesn't depend on that. So for this one, it will be considered independent event. All right, let's do this last one. So your favorite color is blue and your friend's favorite hobby is fishing. So we have your favorite color. So you selected blue. And then your friend's favorite hobby. So for favorite hobby is fishing. So does the fact that your favorite color is blue have any influence that your friend's favorite hobby is fishing?
No.
No. So for this one, this will also be considered independent. All right, so that's it for independent, dependent. So independent just means that one event doesn't influence the other event, but dependent means that one event will influence the other event from occurring.
Okay.
Any question in regard to that so far? All right, so let's go ahead and do this first problem. So here's the formula for the multiplication rule. So for the multiplication rule, this is going to be a little bit different because usually we're doing one selection, but for this case scenario, we're doing two selection. So instead of me randomly selecting one person or one object, we're going to be randomly selecting two person in this case scenario. So what the multiplication rule said, if I want to find the probability of A and B occurring, all we have to do is multiply by the probability of A and the probability of B. So let's go ahead and we're going to test out that formula with this next problem. So for the next one, I said if the probability that person A will be alive in 20 years is 0.7, and the probability that person B will be alive in 20 years is 0.5. So the part A says, is person A independent from person B? So for this one, does the fact that person A will live, does that affect the probability that person B will live?
No.
No, why not?
There's two different people. There's no like evidence that they have a connection.
Yeah, so they're two different people, so there's no evidence they have a connection. So if one person lived for 20 years, that doesn't make it more or less likely that person B will live for 20 years. So we'll say they are independent So that's it for A. Let's do B. So for B, it says, what is the probability they will both be alive in 20 years? So if you notice for this one, we want both of them to be alive in 20 years. So we're doing two selection. So we want the first person to be alive. And we're going to say this is person A. Then what we want person B to also be alive. So what we have to do, we have to find the probability person A will be alive. And we want to multiply that by the probability that person B will be alive also. So what's the probability that person A will be alive in 20 years? And if you want, you can type it into the chat. Ooh, 0.7. Perfect. So 0.7. What's the probability that person B will be alive? Cool. So if we multiply this out, we get 0.35, or you could say 35%. And that's it for part B. So that's how the multiplication rule works. You have to just multiply those two independent probability. And then whatever you get, that's the probability that those two events will happen at the same time.
Wait, how did you get the 0.7, 0.5?
So the 0.7, if you remember, the 0.7 is here.
Oh, okay, okay.
The 0.5 is right over here.
Okay, I got it. Never mind.
Yeah. Any other question for this example? Okay. So we're gonna do one that's not on the notes. For that way you can kind of see how this formula works. So what we're gonna do, here, let's do flipping a coin. And what we're gonna do, we're gonna flip the coin 3 times. So what we wanna do, we're gonna get the sample space. So in case you forgot what the sample space is, the sample space when we just list out all of the possible outcomes when doing this. Okay, so I'll get it started. So one of the outcomes that could occur if I flip a coin 3 times, the first time it can land on heads, the second time it can land on heads, the third time it can land on heads. So that's one outcome. What's the other outcome that could occur? And if you want, you can put it on the chat or just vocalize it.
Maybe like tails, tails, tails.
Cool. So we'll do tails, tails, tails. All right. What's the other outcome that could occur?
Heads, tails, heads.
Heads, tails, heads. You can also get tails, heads, heads. And lastly, heads, heads, tail. Or you could get tail, tail, heads, tails, heads, tail, and lastly, heads, tail, tail. Cool. So that's my sample space, correct?
Mm-hmm.
All right. So say if I want to find the probability that the coin, when I flip it 3 times, it lands on H, H, T. Actually, let me rewrite this. So we want to find that the first time it land on H, the second time it land on H, and then the third time it land on tail. All right. So how many outcome in our sample space give me HHT in that order?
1.
Yeah, so there's 1. Out of how many total?
8.
8. Cool. So you get 1 out of 8. But there's actually an easier way to do this. So the way that we could do this is by using the multiplication rule. So we're going to find probability of H and T. Because first off, when I flip the coin 3 times, are all of the time that I flip it, are they independent from each other? Or like say if I land on a head, does it make it more likely I can land on heads the second time around and the third time around?
No.
So this should be independent, correct?
Yes.
It doesn't matter if the first time it land on heads or the second time it land on heads. The probability that the third time it will land on heads will still be 50%. So they're independent. So what we could do, we could say probability of heads, and you multiply it by the probability the second one will be heads, times the probability the third one will be tails. So what's the probability that it will land on heads?
1/2.
Yeah, 1/2. What's the probability that the second time I flip it will land on heads? Well, it will still be the same, 1/2. What about the probability it will land on tails? It will still be 1/2. So if I do 1 times 1 times 1, what would that give me?
1.
Perfect, 1. What about if I do 2 times 2 times 2?
6.
Multiply.
Oh shit. Give me a second.
Take as
8.
seconds as you want.
8.
8.
Sorry.
No,
Brain
it's fine.
fart.
We all get them. So if you kind of notice, we got the same answer that we got when we did the sample space. So that's why the independent rule, we use it, or the multiplication rule, that's why we use it. It is a faster way how to get the probability. As long as we know they're independent from each other, you could always use the multiplication rule.
Okay.
All right, so I'm gonna go back to my notes and we're gonna do some problem in my notes. All right, so let's do this first problem. So it says the probability that a randomly selected male age 60-year-old will survive the year is 92.186%, according to the National Vital Statistic Report. Part A said, what is the probability that 2 randomly selected 60-year-old male will survive the year? So for this one, how many 60-year-old male are we selecting?
2.
Cool. So we're selecting 2. And for this one, can I assume that the 2 60-year-old male are independent from each other? Yeah, so we can assume they're independent. And the reason why we're assuming they're independent, because we got like one 60-year-old male shouldn't influence the life of a second 60-year-old male. Like they're independent from each other. All right, so for this one, we want both of them to what, survive or not to survive?
To survive.
Yeah, so we want the first one to survive, but we also want the second one to survive. So since we have 2 independent events, and since we're doing 2 selection, we're gonna get the probability the first person survive, and we're gonna multiply that by the probability the second person survive. So the probability the first person survive is 0.92186. And then the probability the second person survive is 0.92186. So we're gonna go ahead and multiply that out. So let me share my calculator. So you should see a calculator right now. So we're gonna do 0.92186. And we're gonna multiply it by itself. So we do times 0.92186. And you should get the probability that the first one survive and the second 60-year-old male survive, it's 0.8498. And that's your final answer for that part A. Any question in regard to part A? All right, so let's go back to the notes. All right, so let's do part B. So for part B, it says, what are the probability that two random 60-year-old male will not survive the year? So for this one, we want both of them not to survive. So you want the first one not to survive. And we want the second one not to survive.
This is getting a little too real.
I know. We should have done this a little bit earlier in the class, not after the coronavirus. Okay, so how would I do this problem? So instead of I wanting them to survive, I want them not to survive. So I know the probability they survive is 0.92186. So if I want to find the probability that they don't survive, how can I do that? Well, let's kind of think about it. Like, if I tell you the probability it's going to rain today, it looked pretty cloudy, we'll say 60%. If I want
You
to
subtract it?
Yeah, so I subtract it from what?
100?
100, perfect. So we do 1 minus 0.60, and you get 0.40. So if I want to find the probability that somebody does not survive, how would I do that?
Do you subtract 100 from the 92?
Perfect. So we do 1 minus 0.92186. And let me see, what does that give me? So 1. So we get 0.07814. So now what we're going to do, we're going to do 0.07814, but we're going to multiply it by itself again because we want both of them not to survive. All right, so let me share my calculator with you so that we can see how to do it. So on the calculator, you can say 0.07, 814, and multiply it by itself by 0.07814, multiply and times each other, and you get 0.006, I will say 1. And that's your answer. So if you look at it, it's not very likely for both of them not to survive. It's more likely both of them survive versus them not surviving. All right, and that's it for that part B. Any question for part B? So what I want you to do, I want you to try this problem. So let's try this problem, and after we're done with this problem, we'll just call it a day. For that way, you're not overwhelmed. So try doing this one. This is a light-hearted problem. It's about baby's eyes, so no killing. So should be fun.
Nice. Oh no.
There you go, your green eyes. Well, one eye.
So it's 0.06 times 0.06.
Perfect. Yeah, so for this one, you want the probability the first baby have green eye, and you want the probability the second baby have green eye. So that's 0.06 multiplied by 0.06. And when you multiply those two out, what do we get? So what's 0.06 times 0.06?
I don't know.
36.
Perfect. All right, so that's A. All right, so try doing B.
Is it 0.0564?
Let me double check that. Yeah, good.
Because it's 94% times 0.06%, right?
Yeah. So if you multiply that out, you get the 0.0564.
Damn, big math. Big math.
Very cool. And that's it for that problem.
Where'd the 94% come from?
So the 94%, because we want the first baby not to have green eye, correct?
Okay.
So if you know the probability they have green eye is 0.06, the probability they don't have green eye or not green is equal to 1 minus the 0.06, which will give you the 0.94.
Okay.
Yeah, so that's where the 0.94 comes from. It's like they're just two mutually exclusive events because either the baby have green eye or the baby doesn't have green eye. So that's why you say 0.06 is the probability they have green eye, and 0.94 the probability they don't have green eye.
Can you scroll down? I want to copy that.
Scroll down or up?
Well, like, no, wait, no. Up. Yeah, there you go. Thank you.
Yeah. All right. Any other question in regard to this problem?
No.
All right. So what we're gonna do, we're gonna stop right here.